Today we will continue with random walks and their applications. So before we move on, let me provide you some references for the previous two lectures as well as this one and the coming one. So some of the slides I have taken are from Purnamrita Sarkar and another one which is from a book. So I am using them. For references, random walk, there is a very good survey by Lovaas. It's called Random Walks on Graphs, a survey. What I have covered is basically section 1, that is introduction, and part of section 2. But it goes on into much more detailed analysis of random walks and many other interesting properties. You could also look at section 3, just the beginning of it. For PageRank, of course, the Wikipedia page on PageRank is quite informative and it has further links to other material. Moreover, there are very good websites which simulate PageRank. So you can give a graph and ask it to simulate for 1 iteration, 2 iteration and so on, so that you can get a feel of how PageRank works. So you can go through that. And also there is this paper, it's called this $25 million eigenvector, the linear algebra behind Google. So this is also an interesting paper in the sense that they explain the basics, it explains the basics very well. But you know, PageRank has a lot of references. So you can go through, you can search for yourself also. And HITS, you could go through the paper by Kleinberg himself, which was published in Journal of SEM. And this is a very accessible paper. That's why I have you know, given the reference to this particular paper. It covers almost everything that I have talked of in much more detail, and it's very much readable. So I would definitely recommend that you read that paper. So yesterday we discussed the HITS algorithm, and today we will see the application of HITS on a slightly different network. Yesterday we saw it on the web graph, and then it's used for ranking the web pages. Let's see what's the connotation of HITS when we apply it on a citation network. So what is a citation network? You have nodes which are articles. So say A4 cites A1 and A2, and all of them cite A3. So suppose this is a very small citation network. Now what do you do in HITS? So you compute two matrices. Assume that W is the link matrix for this citation network. Yesterday we used a slightly different symbol. We used A for it, the adjacency matrix. Suppose we represent the adjacency matrix by W. Then remember, we computed two eigenvectors, one which represented the hub scores and one which represented the authority scores. And one was the principal eigenvector of W transpose W, and the other was W W transpose. So here there is this concept of co-citation network or co-citation matrix, which is W transpose W. So let's see what W transpose W means. So what is W? So or rather, what is Wij? It is 1 if Ai cites Aj. This is the semantics of Wij. That's how we define this citation network and therefore this citation matrix. Now what happens when we compute W transpose W? Tell me, what is Aij? An element of this A matrix. It is Is it clear? It's a very simple expansion of matrix multiplication. So what is this particular element? Wik and transpose. Is it this? Wik transpose is nothing but Wki. Okay. So, basically you are counting Wki, Wkj, the summation when k varies from 1 to n. So, then in the co-citation network, the edge between say a particular node ai and aj represents what? Is it? So, suppose k is a paper, ak is a paper, then when is this 1? K should cite this as well as k should cite this, then Wki is 1 as well as Wkj is 1. So, basically it counts how many such k's are there in the co-citation network. So, it counts the number of articles which cites both I and j. So, how many articles are there where both I and j are cited. So, this is the co-citation matrix, and you could very easily see that this matrix is symmetric. So, the number of articles that are cited by that cites I and j together is same as the number of articles which cites j and I together. So, it is an undirected network, it is a symmetric undirected network. So, that is the semantics of Aij, and the corresponding H matrix, which is also called the hub matrix or the bibliographic coupling matrix in the specific case of citation networks, is defined as W transpose. So, if you compute for this, what is your Hij? Right. So, basically what it means is how many common citations does this particular article AI and AJ has. So, if AI has cited 10 articles and AJ has cited 10 other articles, there is an intersection. So, what's that intersection? So, that is called bibliographic coupling between articles, and that is the definition of this particular hub matrix. So, these are very well studied matrices in the scientific literature, both co-citation and bibliographic coupling matrix. But can you now use this concept to identify what actually W transpose and W transpose W, the authority and hub matrices in the case of web meant? Not necessarily. Yeah, what that really meant. So, if you have a graph like this, so this is I, say a web page I, and this is a web page j. So, in the matrix W transpose or in the corresponding hub matrix, as I say, what would it mean? Means what's the strength of this particular link? Isn't it the number of nodes to which both of them point to? By the same analogy, right, is the number of nodes which both of them point to. So, if you think of doing a random walk on this hub matrix, what you are essentially doing is you are going one step forward and one step backward, one step forward and one step backward, and this whole thing is one step in the random walk. Do you get it? So, usually if you do a random walk only on the matrix as you do only on the graph as you do for page rank, you do the random walk in this way. You go from here to here, then from here to somewhere else, then somewhere else, and you trace a path like this. So, every hop is a step in the random walk. But when you do hits or hits algorithm, basically every traversing one node to other node is not a step in the random walk. One step, remember you are computing a hub score, then recursively the authority score, using that score again to compute the hub score. So, what this physically imply is you are computing a random walk on this particular hub matrix to compute the hub scores. You are doing a random walk on the hub matrix, and this hub matrix is nothing but if there is n such nodes to which both wi and wj point to, then the weight between wi and wj will be n. Again, this is also a symmetric matrix. WW transpose is a symmetric matrix.
So one may think of this graph as a directed structural equivalence.
So what one may think of is that it's a two-step. So in the real graph, there is a two-step process which kind of is modeled as a random walk in this modified graph. So if you look at the corresponding random walk on the real graph, you are going to a node and traversing a backlink, one forward link and one backlink, and that's one step of your random walk.
There is no arrow from back from K to J. When you say traversing back, there should be a from K.
No, that's why that's what I'm saying. There is no link between K to J. That's why it's called a backward direction. You are traversing a link in the backward direction. You mean, right? Yeah, you understand that going through a link in the forward direction is you go from J to K, and backward direction is from K to J. So it's not a random surfer. The random surfer can't come back unless he presses the back button of the, and if even you press the back button, you will come back to the same node. But here it's not like that. If you could go from I to K, but in the next step you will not go from K to, say, this is Wk and this is some W m, you will not go to Wm. You have to go to, you traverse a backlink, a link backward. So you might come to Wi again or Wj again, and that's your one step. And what happens when you do the authority step? When you compute the eigenvectors for the authority, what is the physical correlate for that random walk? The first link you traverse is backward, and the second one is forward. Remember, while we computed the A matrix, it is something like this. So you computed how many such nodes or web pages Wk exist, right? And that's what is actually the modified link between these two. So the link between these two is number of such Wks. So essentially, what you are doing when you are doing the random walk is you are coming back one link and then going forward, and that gives you a direct. So when you want to go from Wi to Wj, you are doing this kind of a traversal. So the first link is backward and the next link is forward. But mind you, there is a difference. In the original random walk, as in case of PageRank, it's a stochastic process. So the probabilities are very nice, they sum up to 1. Here, if you see the WWT matrix, it's not a Markov matrix. The rows will not sum up to 1 or the columns will not sum up to 1, right? So it's not a stochastic matrix. So that's why hits is not directly, means you can't relate hits to a random walk as such. It's called a reinforcement algorithm. So the hub scores reinforces the authority score reinforces the hub score. It's not a random walk. So I am just trying to motivate you that we could think of it as a random walk, and if we do that, we get a different algorithm. It's called SALSA. We'll come to that algorithm just in the next step. So if that is the case, then what happens when we do a random walk? By random walk, I mean, you build this new graph, the authority graph or the hub graph, and do everything probabilistically. Means your probability, the whole method is now a Markov chain. The probability is sum to 1 and all these properties should be valid. Then what do you get? So the algorithm that you get is called SALSA, and it was just published, the Kleinbach paper, the first one in 98 and the second one was published in 99, the Journal of ACM, the extended version. This was just published after that. These guys, what they do, so this is the name, Lempel and Moran. They published it in 2000. They saw Kleinbach's algorithm and they immediately realized that he is trying to do a random walk, but he is not normalizing the probabilities and all. So it's a reinforcement algorithm and not really a random walk. So they say, let's do the corresponding random walk version and let's see what we get. So it's just a probabilistic extension of the hits algorithm, and as I said, the random walk is carried in 2 steps. So you go forward one link and then traverse a link backward. So, and there are two random walks, one is the hub walk and one is the authority walk. In the hub walk you go one forward, one backward, in the authority one backward and then one forward and so on. So, that is what is written here. I have already discussed this. Let us see what it means. So, there are many ways of visualizing it. I already gave you one visualization. There is another possible visualization using a bipartite network. So, we said that every node is a potential hub and a potential authority. To start with, you do not know which is a hub and which is a authority. So, for every node you replicate the node. Suppose there is a node 1, you make two nodes out of it, 1H and 1A. You assume that 1H is the hub version of this node and 1A is the authority version of this node. Similarly, for 2 you have 2H and 2A and so on. So, for all the nodes. So, there should be a node here 3H. Why there is no 3H? 3 has no out degree link. So, essentially its hub score has to be 0. So, therefore, they do not put it, but you could assume a node standing there with no connections. They do not want the graph to be disconnected because of the reasons we described earlier. If it is disconnected, your eigenvectors will not be unique, the stationary distribution will not be unique. So, to make it unique, they enforce that the graph is connected. So, nodes which does not have out degrees, outgoing links, and can't be there in the hub place, and nodes which does not have in degrees can't be there in the authority space. So, I think 4 does not have any incoming link, so 4 is not there here. So, they construct these nodes, and now for every edge what they do, suppose there is an edge from 2 to 1, then that edge translates here as an edge from 2 hub to 1 authority. So, 2H to 1A. If there was an edge from 1 to 2, what would have happened? 1 hub to 2A, but there is no such edge. So, they do not add it. So, similarly for every edge you get a corresponding version here. So, this is a bipartite graph which they call means on which they do the random walk. It is easier to visualize. And then they define the hub and authority matrices as we did earlier, but in this case it is not simply a multiplication of A transpose or A transpose A, they do more. What they have to do? They have to normalize, right. So, let us look in the previous slide. How would the normalization go on? Say consider 2H. So, there are 3 things going out of it, right. One goes to 1A, one goes to 5A, one goes to 6A. So, if you want to traverse from 2H to any of these nodes, what is the probability on each of these edges? 1 by 3. If it is a Markov process, all of them have to add to 1, so it is 1 by 3. So, instead of 1 by 3, the general thing would be 1 by the out degree. K is what? The out degree of the node 2. So, let me call it K out of the node 2, or let me call it D out of node 2. So, all of them is like this. So, D out of node 2 is the out degree of the node 2 in this graph, and you have 1 by that. So, that you have. When you go from actually in the reverse direction, suppose you are going from 1A to 2H or 1A to 6H, then what is the normalizing factor? 1 by in degree of that particular node. So, whenever you are normalizing the authority part, you are dividing by the in degree. Whenever you are normalizing the hub part, you are dividing by the out degree of that particular node. So, if you do so, remember I said it is a step random walk, right. So, for the hub matrix, you go from, you start from a node here, you go there and then again come back to a node here, right. So, what is the probability that you start from node say to H, sorry, let me put here I, okay, 2 is fine, and we come back to a node say 6H. What's that probability? How do you compute it? So, it can happen in many ways. So, suppose there is a node which I call 1A. So, you could come to 1A and then go here. The probability of coming to 1A is 1 by d out of 2, and this is 1 by d out of d in of 1, right. And now suppose there is another node here, say another node here. This is 1A, this is node 1. So, you are going from 1 to 6. So, that is why you will normalize by the out degree of in degree of 1. Now, suppose there is another node here, call it is there anything else in this picture? There is no other common node between 2 and 6, but suppose there is something called 8A here, and again there is this edges. So, coming down this is always d out 2, but going back is now 1 by d in 8. So, can you write the formula for what is the probability that you go from 2 to 6 in the hub walk? 1 by dn comes as the common factor, sorry, d out 2, and then you do sigma of over all k's, k is equal to 1 to n, 1 by d in of k. Is it clear? Provided that the edge exists, provided that the edge exists. So, let me rather than this replace it by provided that there is an edge between say 1A and 1k. So, there is an edge between 1 and k, and there is an edge between k to 6 in this particular case. So, you could replace them by ij and get the general formula. So, this is the general formula. So, there is an edge from h to k and k to j. So, k to j you could replace by j to k, because in this bipartite network it is no longer directed. You do not need the directed edges, because you already have defined the nodes as hubs and authorities. So, you know the semantics of each edge, they runs between from hub to authority. So, therefore, you do not need that. And of course, you multiply, you normalize it by degree of 1 by IH into 1 by K. Now, I is actually, this is common factor, it can come out and you can do that, right. So, that is how the hub matrix is defined, it is a 2-step random walk. And in the same way, very symmetric way, you could define the authority matrix. So, here what happens is you have, by the way, so in degree of this particular node in the original graph is nothing but the degree of the corresponding A node in the bipartite network. So, in degree of node 1 is nothing but 2. The in this particular bipartite representation, the degree of this particular node, you can check that. So, there are 2 edges coming to 1, and out degree is simply the corresponding edge version. So, IH. So, that is why we wrote in degree and out degree, instead they used this whether it is IH or KA. So, they used the other thing. So, IH is out degree of I and KA is in degree of K. So, we used that particular notation. So, in this way you can define the hub and authority matrix. Now, you could see that hub matrix can also be written in this manner. Think of 2 new matrices WR and WC. We define a new matrix called WR, where we normalize the row sums. So, we make all the rows equal to 1. We add the degree of the node. So, the row would be the out degree and divide every element by that particular term. So, it is the row stochastic matrix, corresponding row stochastic matrix. Is it clear? Let me just take one example and Suppose this is your original matrix, okay. So just ignore it. So what is the corresponding row? So suppose this is W, then what is the corresponding row stochastic matrix? WR. WR is, for every row you check the sum. So in this row it's 2, the sum of the row. So you divide it by 2. So it's 0, it's half, it's half, it's 0. Then it's half, 0, half, 0, 0, 0, 0. This is 1, not half. And this is exactly, okay. And what's the corresponding? WC is the corresponding column stochastic matrix. You divide all the columns by the corresponding in degrees. So what will be this particular row? So sorry, this particular column is this. This is also same. What's about the next one? And last one, right. So this is the definition of WC and WR. And now you can easily see that the hub matrix that we defined previously, remember, by this definition can also be written as WR WC transpose, whereas the authority matrix is WC transpose WR. So do you want me to derive that part also? It's like pretty obvious, you could see that, but that's not important. What is important is, let me ask you this, how it is different from the original Hits algorithm. So in original Hits algorithm also you had a hub and authority matrix. What's the difference? Instead of WWT, now you have WRWCT by T I mean transpose, and instead of W transpose WR, so basically W's are represented by WR and WC depending on the case you are looking at. Okay. So now let us define a particular thing. So this is the in degree and out degree in the original graph, which is nothing but this degree. So you can just ignore this part. Look at this. What's the sum of in degrees of all the nodes here? What is the sum of in degrees of all the nodes here for the original graph? Can you relate it to some property of the original graph? So I am asking, in this particular graph, sum of all the hub nodes, say 1H, 2H, the degrees of all the hub nodes is equal to what of this graph? What property of this graph? That's the number of edges. It's clear to everybody that that's the number of edges. And what about the sum of the degrees of all these A nodes? No, it's the number of edges, not twice the number of edges. So in any bipartite network, the sum of the degrees of one partition must be equal to the sum of the degrees of other partition. Any edge that leaves here has to go there. So you can't have one edge leaving and two going there, so that it becomes twice. So this particular quantity W is nothing but the number of, this is another strange W, curly W, which is nothing but the number of edges in this particular network. Now comes the real punch. So when you do all the analysis of this Salsa algorithm, you can show this particular theorem. Whenever MA is nothing but the authority matrix. He has used different symbol. I have taken all this from the original paper. So he has used slightly different symbol in different parts. MA is the corresponding authority matrix. So if the authority matrix is an irreducible chain, by irreducible chain it means it's a single component, means you have a unique eigenvector. So it has a unique stationary distribution, which is true obviously, and suppose that distribution is this pi. So pi 1, pi and all, then you have pi I, that is the ith component of that eigenvector, or the probability of the stationary distribution during the stationary state, steady state being at particular node I, is nothing but the in degree of I. W is only for normalization. So, it is nothing but the in degree of I by W for all I in A. So, why is this? Okay, first of all, proving it and all will come to, but let me ask you this question: why do you find this result as a punch? Don't you find like we have been firing a cannon to just kill a mosquito? We have been trying to do page rank, then we came to hits, and then we tried to modify further hits and came up with salsa, and then we found what solves all the thing, it's ranking just based on in degrees. So, the hub score is nothing but the in degree, sorry, the authority score is nothing but the in degree, and the hub score similarly is nothing but the out degree. So, all our effort went in vain, is it? We will prove it later, but first try to grasp this fact. Yeah, it's true, but we will always want to have a connected graph. We will always want to have a connected graph. Okay, so let me tell you the fact. There is no hidden thing here. It's written clear and straight, and if you read the original paper, these guys also say this, that ultimately what works is degree. So, basically they say that salsa is much better than hits because you do not need to do the iterative computation, it is just one step process. You calculate the degrees and assign the hubs and authority score, and they showed that their method works better than the original hits algorithm just by looking at the degree. But then if you look at the history of how this field progressed, it is really interesting. The first thing that came to people's mind was degree itself. Remember the first time I asked about that web page ranking or information percolation, all of you immediately replied with degree centrality, and indeed degree centrality works to some extent, but it has some problems. So, initially people started with degree centrality, and then people came up with page rank and hits which are supposed to work better than degree centrality, and then we slightly modified hits more, and then suddenly we realized, oh no, degree was better, then how come we were mistaken? And how come we were mistaken is also an historical fact. So,
do we have a proof for the fact that hits is better than degree centrality?
So the proof is all empirical. So, what you do is you apply, so if you look at all these papers, what they do is they will apply it to some real data and show that so what hits showed is page rank does this and I do this, so mine is better on some pages. And what then this salsa people did is hits give give this as the hub score and authority score, and I do it, my algorithm gives this, which is much better. So, you prove it in this way, and when they did the analysis after that, initially they were very happy with the algorithm and that they got good results. When they did the analysis, they found that it is nothing but the degree that they are counting. So, they do not need to do any iteration and anything. Now, at this point of time, when they tried to investigate what went wrong, if anything, then they realized actually all these algorithms. So, remember somebody asked this question in previous day, that all these are ignorant to queries. What is the real query? And unless we look at the real query, page rank does not make much sense, hits does not make much sense. So, all these guys were working with already available search engines. So, what happened? Kleinberg showed that hits was working better compared to Alta Vista results. So, he took Alta Vista's results and re-ranked them and showed hits was better. So, salsa people showed, of course, at that time Google was not there, 2000 I am talking of. So, they showed that whatever the prominent search engine at that time, salsa could do better than that. So, they were forgetting the fact that the original search engine historically also developed, the query part was also developing. So, since the query part, you see what I mean by the query part. So, the query processing part, how you look at the text, how you, so if all these things are excellent, you could, there are many other error removal, noise removal things. So, the first noise removal thing is if a lot of pages point to each other, in the sense internal links which we call. So, IIT Kharagpur has internal links to departments, department has internal links to faculty, and faculty might have back again links to department and then institute and so on. So if you remove all these internal links, because internal links actually introduce a lot of it's an effect called tightly knit community effect. We'll look at that. So all these problems, if you remove and then get a nice query graph and all, on this you apply this salsa, then it works better than HITS. So that was their final realization. But of course this also has a problem. And when you say if we can prove anything, the only other thing we can prove is that under certain condition, if there is a tightly knit community. So remember the definition of tightly knit community that I talked about last day. It doesn't work well on tightly knit community. You don't remember. So suppose there are 10 nodes here and some 5,000 nodes here. Since there are 10 nodes, actually there are 5 which are very good. It's a say K55. So it's a complete bipartite network. So all these gets an extremely good hub score and rest gets extremely good authority score. Whereas here, since it's a huge graph, even if it has a high degree, there is some very good hub, but these all of them might not be good authority and all, and since you normalize, it spreads out. The goodness of the score spreads out. So empirically, if you see the HIT score gives high scores, hub scores and authority scores to such tightly knit community compared to the whole web, whereas the bigger community might have been much better. Actually, if you see, there are very good pages out there, but they get less scores. So this is called the tightly knit community effect, TKC effect. So you could prove one thing mathematically, that salsa is more immune to TKC. And this is because here you are looking at degrees, and if you look at the bigger community, there will be more degrees than the smaller community. Here the degrees are 5, but hub scores can be very high, whereas here the degrees may be 10 and salsa will give it higher score. So that's another provably good thing about salsa. Okay, but now can you relate this to any previous theorem that we have already proved, this particular thing? This proposition 1. So I am saying the stationary distribution is equal to degree by some normalizing factor. So can you recall some property of graphs which we already proved using this? You forgot again? So remember, in the very beginning, means the first lecture on random walk, we described that suppose A is a undirected graph and M is the corresponding Markov matrix. Then what is the first eigenvector of M? The principal eigenvector of M. And we could prove that that is equal to the steady state distribution was equal to the degrees of the node. Do you remember that? If you don't, you just go back and look. So we proved that. I am not going to prove it again here. So it's almost the same thing repeating, and the proof is also similar, slightly involved. So I will give you the sketch of the proof. So let's prove it for the hub. Right. So Hij what is this? So suppose A is the original, okay, A they have used for something else. So W is the original adjacency matrix of the graph. Then, so Wik by, what is the normalizing factor? You see that? And this is what? So, up to this much, is it clear? So, this is a row normalized matrix, remember WR. So, WRIK will be normalized by the row. So, the row is I, and when we normalize the row, it is the in degree, sorry, out degree. So, it is the out degree of the node I by which you normalize, and when we normalize the column, it is the in degree of the column node. So, K is the column node. So, you divide it by the in degree of the column node. So, you get it. So, this is one particular node, and here you can actually take one thing only common. This does not depend on the summation. So, this is what you get. Okay. So, this is your Hij. So, if you multiply now the Hij, your H matrix, with your pi matrix. So, you are multiplying this H with this d in degree 1, I am leaving the normalization factor, d in degree n. So, in this matrix, what is the ith term? Say, what is your, in this multiplication, what is your ith term, which I call, let me call it C. So, what is your Zi? Tell me. Sorry, K is equal to 1 to n H I K d in degree k, isn't it? And now you replace H I K with what we derived earlier. So, let me rename it as Q and you have a constant term which is 1 by d in degree out degree of I. So, the out degree of I comes out directly. Anything else that you can bring out? So, summation depends on Q1 to n. So, yeah, nothing else you can bring out. Yeah, d in, sorry, this one, right? You mean to say? So, can we take it out? We can take it out, but place it here, but we can't take it out from the inner sum. Okay. So, this is the form that you get, and now you have to rearrange the sums actually. So, there are two summations and you have to rearrange the sums. If you do that, I am just rewriting what is there in the previous one. So, here you see your I is fixed. Oh, this is k, this is kq, right? The j was k is the variable here. So, here you see your I is fixed. So, you are going from iq and then from kq. So, what is happening if you expand this sum, there are two sums. So, what you can do is, so think of this multiplication terms. So, in one series you will have say I is equal to 1. So, 1 1 and then k is equal to say 1. So, you held k at 1 and I at 1 and you will get one series and so on. The other series you will get, so now you held I at 2 and q at 1. And so on. So, what you can do is, if you write this matrix, now do the sum this wise. I could rewrite it using the forms, but I just wanted to give you a visualization of this. Now, do the sums in this way. So, you can take this part common. So, for this row actually W11 you could take common and you could count all these things W1 1, W2 1 and so on up to Wn1. And what is this sum basically? This is the in degree of this particular node, right, and this particular node is nothing but q. So, this is what will cancel your di and q. So, this di and q factor which I did not write here will get cancelled out in all of them, and this sum actually kind of turns out to be d out I. If you do that, this whole sum, all of them will be 1 actually, there will be multiple ones, and if you do sum all over all those ones, it will come out to be d out I, which will cancel out this d out I, and what you are left with will be your d in I. So, this whole thing will come out as d out I into d in I, and then you have d out I here. So, this will cancel out and finally, it will be equal to d in I. So, this should show you that this is the eigenvector, because you multiplied, you expect Zi to be d in I, because you multiplied with d in I. So, in general for it will be the same vector. So, if you do now h I with this vector d in 1 to d in n, you will get the same one. You could see the paper for the proof. It's like only 5 lines, some algebraic manipulation. This sum, 2 summations, you have to just reorient with and play with the indices a bit to get it. But the visualization you get if you write it out, if you spread it out, and instead of the rows you sum the columns and the things get cancelled. Okay, so that's what is about SALSA, and as we asked, is it good, and we saw that it works fine in the TKC effect, in the presence of the TKC effect. That's one provable thing. Empirically also it's okay, but there are also limitations. So, in general, I will just try to conclude, wrap up the field. So, this whole field of web page ranking, or even ranking nodes in social networks and all, is often termed as link analysis. So, links are basically directed edges. So, the question that link analysis asks is, which directed edges in a network should be given more weight during the random walk. Till now we have been given it based on the simple probabilities. So, if there are n edges, all of them get 1 by n, but sometimes some of the edges you might want to give them much more weight than the others based on some other factors. So, this whole field starting from what I already talked about, page rank, hits, these are the core foundational work of link analysis, and people are still working on, it's still a very active area of research. But and I also talked about two more things in link analysis yesterday. So one was the static ranking, remember. So static ranking is a different kind of ranking method where you take page rank or hit scores as an input as well as other features like query related features, and together you make a good kind of aggregation between the two. You weigh them nicely and kind of get the value. There is also another way of doing this kind of aggregations, and this is called there is a method called net ranking. So it's a machine learning technique, and it was developed by Soumen Chakraborty of IIT Bombay. So it's a one of the very celebrated, currently one of the most sophisticated methods of link analysis. So I will just give you the idea what it tries to do. So what you do, you are given a network and you tell the people, tell the algorithm that certain nodes should be ranked higher than certain other nodes. For all nodes you don't give that, but pairs of nodes. And why pairs of nodes? If I give you 10 nodes, it is very difficult for you to put 1, 2, 3, 4, 10, means put them as rank. Even for human beings it's very difficult to adjudge which is a better page, and it might differ from you to me and so on. But if I give you two pages which are quite different in their content for a given query, you could say that this is better than the other. So suppose you give the algorithm say 50 such labeled pairs. Say I give you some 100 pages, 50 pairs of pages, for each of them you say that this is better or that is better. So with that, what the algorithm does, again it does some stochastic random walk kind of thing, but what it does is now all the links, it tries to learn more features. So suppose there is an edge between a node which has very few incoming links and very high outgoing links and so on. So it has a lot of features, you can put your own features, and then it will learn that okay, these edges are always better if we take them on the random walk path, whereas there are some other edges which the algorithm automatically learns are not so good while you do the random walk. So you give them less weight, and in this way the machine automatically learns from these examples. So this is called net ranking. This is like more or less the state of the art in link analysis. And you look at also other things like what's there written on the link itself. So if there is any meta tags or invisible text and so on. So these are some problems with in general link analysis. Let me not go through them in detail. I will just in one line tell you what they are. So often if you look at what is written on the link, that might be misleading. It doesn't work. And as I said, tightly knit community effect. So you can try to increase the rank of your own home page by doing all sorts of stuffs. So you could fool all of these algorithms easily. Then sometimes stability is a big problem. So more sophisticated the algorithm is, sometimes it might so happen that yes, algorithm is nice, fast and everything, but it's not stable. If the the graph changes a little, the ranks change a lot. Such algorithms are not good enough. Then a general problem with random walk is topic drift. If you surf from one page to another and so on as a random surfer, do you think you will keep yourself on two pages of the same topic? Suppose you are searching on complex networks, then soon you will go to say networks, and from there you will go to suddenly say distributed systems. From there you go to some Kerberos, and from there Greek mythology. So this is called tropic drift. You could go from one to another and so on. So this is another problem of random walk. Content itself changes of the pages. So all these things kind of are important. So that's all for this lecture, where we saw link analysis and some 3-4 algorithms for link analysis. And next we will see some applications of other applications of random walk, especially in clustering.